All right, so we're going to start our brief section on statistics. And the first question is, what is statistics? And so this is a general definition I found. It says statistics is a mathematical subject that concerns the collection, organization, analysis, interpretation, and presentation of data. Basically, statistics, helps us understand sets of data, which could be data about populations, about groups, about anything you can collect data about. Statistics helps us understand data. So, a statistical question could say, how old are the students at Saddleback College? And you could either collect the data from all students, or you could randomly select a group of students and use that to help you understand the bigger population. Versus a not statistical question is just, how old are you? That's just a question I can ask you. That doesn't help me collect lots of data to understand a larger population. So data, the data that we collect and we look at and we analyze, it can be numerical. So somebody's height, somebody's age, somebody's test score, etc. Or data can be categorical. What's your favorite color? What's your nationality? Anything which has a grouping answer instead of a numerical answer. And so we're going to start by looking at categorical data, the common ways that categorical data can be displayed. It can be real graphs, pictographs, bar graphs, or pie graphs. Now, we're going to look at a real graph, but usually you see things in bar graphs and pie graphs. So a real graph means you actually put a picture of the real thing. And so here's an example where there's a tub filled with beads, and you reach in and you grab a whole bunch of beads, and you want to see what you grabbed. And so you actually line up the beads. Those were the number of pink beads, purple beads, yellow beads, green beads. And since you have actually lined up the actual beads that you picked, it is a real graph. Versus a pictograph would be a picture of the beads. So if there was, 1, 2, 3, 4, 5, 6, 7 pink beads, you would just draw 7 pink beads instead of actually putting the 7 pink beads there. So a pictograph would just draw a picture of the thing, versus a bar graph would have different axes where you have the colors on one way and the amount the other way. And so if we had 7 beads, you would simply draw a bar or a rectangle that is 7 high. If we had 3 purple, you would draw a purple bar, which is 3 high. You would draw a yellow, which looks like 5 high, and a red, which is 4 high. So it's simply a picture of how much you got put into bar form. All right, another one would be, here's another one, where these are populations of states, and these are bar graphs which are going sideways. You can decide to go vertically or horizontally just based on the context. Where you have a bar graph here and a pictograph here, they tell you the same thing, where they said each one person represents 1 million people. So this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 million people. That is also about what that says. Bar graphs can also be split into this is what they call a double bar graph, where you take a category and then you split it into subcategories. And so they have categories of age, 16 to 24 or over 25. But then within that, they have then split this data up by men and women. And so it could be the same thing over here where you've got population. You could then split that population further into different age groups or different religions or different genders. You can sub-split every bar into more bars, and you could have double bar graphs or triple bar graphs. Another common way of displaying categorical data is with a pie graph, where you basically shade in the amount of the pie that corresponds to the percent of what you have. So this shows the distribution of U.S. firm sizes from 2015. So if a firm has 1 to 4 employees, it would be shaded that color. And 56% of firms had 1 to 4 employees, and so they would shade in 56% of that circle, or more than half of it. This shows that the blue is firms with 5 to 9 employees, and 19% had that many. And so 50 or more employees is purple, and we can see that only 5% of the U.S. firms met that category. So pie graphs, very common. Now, numerical data, some of this numerical data is going to be very similar to how we represent categorical data, but with some slight differences. So one could be a dot plot, which is, maybe similar to a pictograph, but we're just putting dots. And so here's the example. It says, let's say we have a bag of black-eyed peas and a measuring spoon, and we just scoop out peas with that spoon. You could read this, right? All these pages are right out of your textbook. You could take a look at the pages and come back in. It's all 15.2. And so they did this over and over again. In the first scoop, they got 18 peas, then 19 and 19 and 17 and 19 and 18 and 20. So you just keep scooping peas, and each time you scoop, you count how many peas were in the spoon. And you could see there was a lot of repeat numbers. For example, 18 peas were scooped 1, 2, 3, 4, 5, 6, 7, 8, 9 times did we get 18 scoops, which hopefully is what we have up here. 1, 2, 3, 4, 5, 6, 7, 8, 9 times. And so on the one hand, this tells you the number of peas in the scoop down here, and then the height up here tells you the number of times that thing occurred. It'd be a dot plot. And then you could also take this and you could put it into a line graph, but we're going to see that in just a moment. So here is another dot plot right here. And you can read all the specifics, but a dot plot, has all the little dots, versus if you turn those into rectangles, now all of a sudden it's a histogram. The difference is a histogram and a bar graph are really similar, but histograms are meant for showing numerical data, and bar graphs are meant for showing categorical data. But they're going to look really, really similar. All right. Now, here is another one. This is a histogram of the household income for the United States. Now, these have to be categories. And so let's see, I think this is, right here would be 60,000. Right here would be 70,000. And so this represents people or families that made between $50,000 and $60,000 that year. And so if we were to come over here, you could see that that's about 9%, because this is percentages of households. So about 9% of households, sorry about that, made between 50 and 60,000, right? And so you still have to split it up. So each category, on a histogram, there still has to be a range of values down here. Because if you said, how many households made exactly 50,000? Well, maybe only one or maybe none of them. And so you want to have a width down here so that your data becomes meaningful. All right, scrolling up. Another way we can show numerical data is with a line graph, and that would look something like this. And so one of the things with line graphs is, in this case, these are average math scores of 9-year-old students on some math test. And so in 1986, they had this score. In 1990, they had this score. Now, I could, put bars here or a histogram here. You could do that kind of stuff. But a line plot is helpful if you want to look at trends. Like, for example, I don't have any data for 2002, but this line helps me see where that might be. And so that's just assuming that there is some sort of trend in this line, and 2002 doesn't go crazy high or crazy low. For example, on here, if I were to take the middle of each of these categories and connect them with a line, we could hopefully see a trend in that line, which would help us predict what may be happening in certain values. Now, to contrast that, line plots are not good for categorical data. Right, if this is looking at populations, we've got Georgia's population right here, or Washington's population right here. It makes no sense to say, hey, what's the population of the state between Georgia and Washington? Because there is no state between Georgia and Washington that makes this. Versus up here, the years progress, 1986, 1987, 1988, 1990. Right, there is no Georgia to Washington state progression. The organization of the categories here is or can be completely random. And then the last kind of data we're going to look at is scatter plots. Scatter plots would take two different numerical values. And so this is proficiency in reading and proficiency in math. So each dot would represent one student. And so it's like this student got this score on reading and this score on math. And so it takes one dot to represent one person or one set of data. And so this dot would say that that student got this reading score and this math score. Now, one of the things that's nice with scatter plots is you can sort of see trends, like this data generally looks like it's going this direction. And so this shows correlation, which says as scores in reading go this direction, scores in math go this direction, or vice versa. As math scores go this direction, reading scores tend to go this direction. The data is correlated together. That is not the same as causality or causation. That does not mean if you increase reading scores, that will by default automatically increase math scores. There is so much other stuff going on here. Right? Because otherwise you could just say, well, I'm going to always focus on my reading and never do any math because I know if I increase reading, it will increase math, but that is not true, right? This is not a causality, it's just a correlation. And so both of these things go up together because there's probably an underlying factor, which is really, really, really good students. Students who work really hard may tend to be good in both math and reading. And students who do not work very hard or for a variety of other reasons may have lower scores in both. But there's so much other stuff going on in here, you can't always just say one impacts the other. There's a pretty classic statistical test that was misinterpreted poorly, and I always remember there was a scatter plot, which looked something like this, and it was about state spending and AP test scores for high schools. And the data went down like this. And so some people wanted to then make the conclusion that if you spend more money, AP scores go down. Therefore, they said, well, let's spend less money and AP scores should then go up, which is completely false. Right? That was just a correlation, but you need to understand the data to make sense of it. Because what was actually happening was states that spend more money actually increased their AP class offerings. So states who spent very little money maybe just had one AP class for the whole school, in which case they were, maybe the top math students taking the AP test, so they had a high score. And states who spent lots of money maybe had 3 or 4 or 5 AP classes per school. So many students were taking the AP tests, which meant on average the test scores may be going down. So anyway, scatter plots. They're very, very helpful, but you must understand them as correlation, not causation. Okay, so here is some incorrectly displayed data. So first one. It is a pictograph. The trouble is they have used a different picture for every single thing. So what animal is the most? It is the crocodiles. There's 4 of them, yet it shows up as less than the gorillas because the gorillas are much taller. Right? So in a pictograph, all pictures need to be the same height. Otherwise, this is misleading. Makes you think there's the most gorillas. All right, here is a line graph. The trouble is, let's see, these are the percentages of students or children meeting dietary recommendations, and they connected these things with the lines, which means somewhere between fruit and milk, people should be right around here, but there is no category between fruit and milk. So again, this should be something that is done with a bar graph. All right, here is another one where they sort of did a pictograph. And the trouble is that the heights are what are represented, right? The height is this number. This height is this number. However, when they drew these pictures, they drew it not just taller, but wider. So if you were to look at the area of these shapes, it doesn't actually correspond, right? If something goes up, it should simply get taller, not necessarily wider. And so these pictures are misleading. All right, and this last example, says this student interpreted, this is the same like a bean problem. You're scooping out beans with a scoop. And one scoop there was 27 beans, 3 scoops there was 29 beans, lots of scoops there was 30 beans. And the student looked at this and said 1, 3, 7, 7, 5, 1. But that doesn't interpret the data. The data was 27 happened once, 29 happened 3 times, 29, 29, 29. 30 happened 7 times, so it'd be 30, 30, and you'd write out 37 times, right? We didn't get a 1, 3, 7, 7, 5, 1. These correspond to the amount of those things. So this interpretation of those numbers is very unclear. All right, all that said, this is your homework for this section. It's activity 15G, and you are only going to be doing numbers 1, A, B, and C, and number 2, A, B, C, and D, which takes this data, this sample data, and you need to put it into the following displays and answer the questions that are asked about it. And that is it for this video.